No. Um. So today I'm not covering anything new. Today is about, um, the coding options for homework 4. So of the 3 of you who are currently here in one form or another, which of you are planning to do that? Okay, and Dale?
I haven't really decided.
Okay, no. Um, okay, and actually, let's see. What's happening, grade 1, okay. Oh,
Would I be the only one doing it at this point?
actually, both people who are here in the room are also doing it, so,
Okay.
so 3 out of 4. Well, the remaining one has already completed their regular homework 4, so, okay, then that means I have something to talk about today. So, by the way, in general, as we're getting, close to the end, okay, uh, and if you're asking due date for what? Due date for everything. Is Friday, May 12th. Because grades are due in SOAR on following Monday, the 15th. So especially for a class this small, that'll give me enough time to read whatever's left. Okay. So that's your catch-up time. Okay. Now, go for a homework 4. Coding options. There's a few functions that you need to write, and there's a couple helper functions that are provided to you. So this, we give you an overview, and there's one part of the assignment that can be rather challenging, so I want to take some time to talk about that. So first, I get a diagram. Here's how all the functions involved relate to one another. So the top level function is the outputs and inputs. Right, so the input is a symmetric matrix A. So you can assume symmetric. And the output will be a okay. All right, will be a diagonal matrix D that contains the eigenvalues of A on the diagonal. And then Q is orthogonal matrix whose columns are the corresponding eigenvectors. So for its job, the is a sort of decomposition. Since in a symmetric case, the matrix in the middle turns out to be diagonal. Okay. And we're assuming a real symmetric matrix. Everything we do just deals with real numbers and never need to think about complex. Now, so what SimI itself does is very little. Kind of like in the first homework, one of the problems, like 3.2.20 was solve AXB, and it delegated all of its work to Gauss elimination for spec substitution. Same idea here. So what it does is call one of your functions. The U is equal to phi diag. Okay. And so what this does is forms U transpose AU is equal to T. So T is symmetric and tridiagonal, U is orthogonal matrix. Okay. Now. Oh, okay. I want to relate this to things in the book, the textbook that could be helpful. Okay, fine. Algebra, eigenvalues, symmetric eigenvalue problem. Oh, I don't know if I have this as an algorithm in a text, but let's see.
We coded that either in this class or in one of the previous classes.
Well, I think that would only been in this class, but something similar to it. Okay, but I also have, oh, sorry, there's some algorithms. Oh, okay, not this one, but okay. Well, if I look at the QR algorithm, the more general case. Okay, so the closest algorithm to this, 6.3.1, but that is for Hessenberg reduction for general unsymmetric matrix. So here you want to take into account the symmetry. And the fact that you're reducing A to tridiagonal form rather than Hessenberg form. And how you'll do this is Householder matrices. Now this is, yeah, so it's very similar to, I don't recall if I assigned this from in the second homework, Householder QR. It's much like that process, except it eliminates one entry less. Okay, but anyway, you have this algorithm to go on. As far as how the symmetry would be taken into account, actually, there might not be a whole lot you can do to exploit it. What happens is you apply a Householder reflection on the left and also on the right. So what's happening is whatever you're zeroing out below the diagonal will also be zeroed out above the diagonal. And that could be an opportunity to maybe do a little less work. But I'm not too concerned about that. So actually that deals with one of the, there's some questions at the end of the assignment after all the code is dealt with, as far as what can be done to make it more efficient. And this is where you take into account what you know to be zero or non-zero. Okay, so that's the first stage. And then the only other thing that the main function has to do is complete the process. So we have sim QR. So this is a part of the symmetric QR algorithm, and that's going to be applied to a tridiagonal matrix that comes out of a tridiag. Okay. So this does Q transpose PQ is equal to D. But this Q, and it's not the final Q that is passed back as output. It's part of it. So that Q is one that reduces T to diagonal form, but you want to actually, you want the matrix that reduces A to diagonal form. So if you use this equation inside this one, then you can figure out how to get the final Q. So basically, I've written most of the code for you for the main function. There's just one step more. Okay. Um. Now, as for what SimQR does, that's where the hard part is. Um, um, so, so there's pseudocode that's given in there's a document that is posted with the assignment handout. That's pages taken from Golub and Van Loan matrix computations. Since- and this is their algorithm 8.3.3. All right, although it's a little more pseudocoding than you might like. It still leaves a fair amount for you to figure out what to do, but and I've given some discussion of what to do in the assignment handout, which I noticed I'm literally not handing out to anybody, but still it's all a handout. So, okay, so now this algorithm includes the tridiagonal reduction. You're not doing that part because that's already accounted for, but everything else in the algorithm is what you need to implement. So basically, while T is not diagonal, so T comes to you tridiagonal, and you're going to be working on those subdiagonal entries to try to make them sufficiently small, like less than some tolerance in absolute value. And how you're going to do that is to identify a maximal. It's weird that I'm writing lowercase all of a sudden. Not sure why that's happening. A maximal unreduced block of T. Okay, so the idea is T is equal to, it has a thing that having a structure like this. Okay. Okay, so due to symmetry, everything else here would be 0. Okay, so initially, that would be the entire matrix, assuming that the subdiagonal is entirely non-zero. So this, the idea is, this is a diagonal block that is already a diagonal matrix. So it consists of eigenvalues you've already found. Now, at first, this will be 0 by 0. You won't have anything. But as you form QR iterations that make subdiagonal entry 0, a small and growing diagonal portion will begin to appear. So this is unreduced. So that's, and chances are this is going to be 0 by 0 at the beginning also. But the idea is you're going to go up subdiagonal, and as long as subdiagonal entries are 0, you keep going to build up D33. As soon as you find a non-zero subdiagonal entry that is the beginning, the bottom of T22. And then you'll keep going, and as long as you continue to find non-zero subdiagonal entries, T22 will grow until you find an entry that is zero. So that would mark the end of T22, and or you hit the beginning of the matrix. But the top left, in which case there is no T11. There's just this diagonal part and T22. So T22 is what you actually perform work on. So T22 will get overwritten with by this function. QR step. So it's going to take that part out and perform one QR iteration. And this is also from Golub Van Loan 8 point. Oh. For some reason, I don't know if the algorithm identified by number. Okay. Oh, well. But yeah, because I included 2 pages. Okay, so algorithm 8.3.2. Which includes formula for Wilkinson shift and so that one's more cookie cutter. You're just gonna have it do that. Yes. Mhm.
Its dimensions will change as we go.
They will, yes. The most likely thing to happen is that you'll never have a T11. That T22 is initially the whole matrix, and then you make the last entry diagonal, and it gets shrinks by one, by one, by one, by one, every few iterations until you have nothing left. Okay. Now.
It's taking NT to do it.
So sorry, what? Yeah, so it will modify T22. So the idea is, once you get this output here, then what do you do with it? This goes back into the whole matrix.
That is also T22.
It is, yeah. So you take this block out, work on it, and then put the output back. Oh yeah, this is T22. Yeah, so this block goes down here. Yeah. Yeah. Okay, and then this goes back. Yeah. Now, let's see. So then, after that, you go back up top and you're gonna check the whole subdiagonal and see if you've made the whole thing zero. And if so, then you can quit. Okay, now, but one other thing to do is, as you go, want to accumulate these transformations. Now normally that means you just multiply them all together as you go, but so initially Q is going to be identity because you haven't done any transformations yet. Oh, also when this ends, so D will just be T. Because you've reduced T to diagonal form. Okay. Actually, I'm gonna call this Q22 to distinguish from the big Q. Okay. Well, here's where I have to be careful. Q22 is an orthogonal matrix, but it's of the same size as T22. So, yeah, so it is not Q equals Q times Q22 because the sizes don't make sense. However, what I did right there is almost correct. Because what is Q22? Q22 is a product of Gibbons rotations that act on certain columns. So, although it would not make sense to multiply these matrices, you are multiplying something by Q22. And for many to think about, Q22 is acting on what part of this matrix? And so the Q22 acts on the columns of T22. So it's going to be acting on columns of Q also. But which columns? So, yeah, I'll leave that to you to, yeah. I don't know if I have any commentary about that. Okay, I bet it's the same thing in the handout.
But Q22 is a block that is coming from Q, right?
Wait, okay,
Oh, no, wait, okay, oh, no, I'm good.
yeah, it's returned as output from, yeah,
Yes, yeah.
yes. Okay,
This step gives, QR step gives us the. Do we have to build QR step?
well, yeah, QRSF is, yeah, that's a separate function that you implement. And yeah, but you're implementing this algorithm. Do it. So that one's. For most of this, you have pseudocode that lays out most of what you need to do. The only exception of that is this part right here. Identify maximal unreduced block, and the wording in Galois Van Loan isn't helpful either. So, well, I mean, it has a diagram, pretty much exactly like that. So now the handout does have some commentary on what to do, but it basically involves while loops. So you need variables, while loops, yeah. Oh, yeah, that would be strange. So you'd have, so to go these while loops, you want to have variables that hold, like indices. So if you keep in mind that, for example, one thing you could do is have a variable that keeps track of what is the last row of T22. Initially, it would be n. But as you start to find diagonal entries down here, in other words, 0 subdiagonal entries, then you would reduce that bottom row index by 1, and you keep going until you come across a non-zero subdiagonal entry, then you know, okay, that's the last row of T22. And then you can introduce another variable that would be what is the first row of T22. And as long as you're finding non-zero subdiagonal entries from this point, you keep decrementing that. Until you, until it becomes one, in which case you hit the top of the matrix, or until you encounter a zero diagonal entry along here. I suggest diagramming it out. If you implement loops, so you're gonna need two loops, one to detect the bottom of T22 and the other to detect where the top is. First one while loop, then the other. Run your code like on paper on an example, a small example, and see like, is it getting it right? So yeah, yes, it is a pain. So SimI, which is a quickie, SimQR, which is the hardest one, QR step, and TryDiag, which are have decent pseudocode for.
So, for T11, we would only have T11 is like T just so happened to come with zeros at the start of the sub diagonal.
Not necessarily. I've seen it happen. It's kind of weird. Like, okay, it seems like it's zeroing subdiagonal from the bottom on up, but once in a while, some straight subdiagonal entry will become zero. And it's like, oh, how did that happen? But now here's something you can do as an intermediate step. If you decide that you don't really care about this part being where it's unreduced or not, like just find the bottom of T22 and then at least get that to work, produce a correct result. It may not converge as rapidly, but that's possible. And then if you're getting correct eigenvalues and eigenvectors by comparison with what I would do, then put in something to have a check. If you make this to make sure T22 really is unreduced.
Because I mean, I would assume it would take longer, but if you just assume that there's never a T11 and just treat all of it as all the upper part.
That's what I'm suggesting as a first cut. It would take longer, but it's reasonable. Because the odds are against having some entry become zero. Yeah.
Like a small 5x5 block diagram,
Okay.
just as an example.
Yeah.
Just, I want to, it would give you some visual.
Okay. Okay. So your initial T. Okay. All right, I'm going 6x6. Thought might be more interesting. Okay. All right. So the x's are all the non-zeros. So you start at the bottom, you see, oh, this entry right here Okay, so this is T row 6, column 5 is non-zero. So that tells you that that T22 ends at row 6. So scanning from the bottom, if you scan from the bottom up and look for a non-zero subdiagonal entry, the row where you find it is the last row of T22. And then you would see, okay, well, all right, so where is the beginning of T22? Well, it's at the lowest it could be is right here. Good question mark, but then you're gonna look here and see, oh, this is non-zero. So, yeah, so first you think, oh, it's 5, but then this is non-zero. Whoops, I don't want, okay. T4, 5 is not equal to 0, so now you bump it up, now it's 4, and then now you're up here. Okay, and you see, oh, well, but the entry to its left is non-zero. So you keep decreasing that first row until you get to, so you're looking at row 1. So that's the whole matrix. So T22 is seen to identify, occupy rows 1 through 6.
For fun. T4, 3 was 0.
Okay, so if, yeah, yeah. Oh, whoops, I had my indices backwards to T5, 4. And then this is T4, 3. If this had been 0, then that also would have been 0 by symmetry. And now, okay, so, all right. So the top row of T22 is either for 1 or T I plus 1. No. Ti I minus 1. That is non-zero. Wait, equal, that is 0. Yeah. So I'm gonna rewrite this. It's either row 1 or it's row I, where T row I, column I minus 1 is 0.
Yes.
Okay.
I'm glad you changed the lowercase because I was going through here and I was like, I'm gonna mess up. I'm looking and I have like capital T,
Yes.
yeah, capital T22 ends at row 6 because capital T65 doesn't equal 0. But that doesn't make sense.
Okay, yeah, well, that's better to use lowercase to refer to entries.
Yeah,
Yeah.
I don't know why I didn't.
Okay, yeah.
1 second. Just
Okay. Yeah, so in a case where, so now you have this block here at the bottom, unreduced. So you perform QR steps on it until this entry becomes negligibly small. So once T65 is essentially 0, that means that the bottom row of a block capital T22 is now to be less than or equal to 5. Because this, so once this entry becomes 0, then that right there is D33, or the beginning of it.
Oh, yeah.
Because now you have it decouples from the rest of the matrix. Yeah, and actually once that's 0, then that's 0 also. Yeah, yeah. So start from the bottom, scan, subdiagonal. As long as you're finding zeros, you're identifying D33. Once you hit a non-zero, that begins the bottom of T22. As long as it's still non-zero, that grows T22 until you hit a zero or the beginning of the matrix, and that ends T22.
So you don't really have to worry about ever checking past T65, because there's no chance that we're going to mess up the data. Low, so we would just need to check, but we still need to check 5, like T.
Yeah, you don't have to scan from the bottom every time.
Yeah,
If you want to save that location, then you can start your scanning from there next time.
yeah, and we do actually need to still check, because we might have created another 0.
Yes, yeah.
4 might have become.
Exactly, yeah, so you're looking for new zeros. Yeah. Yeah, it's because once you have some decoupling, like whatever you do over here will never affect anything over here. Yeah. And actually, if this is decoupled also, it won't affect over here either. Not like the house anyway, but yeah.
Okay, so we start at the bottom, we scan each entry. If it's 0, then it's part of D.
Yep,
If not, that's where T22 ends.
yes,
Then we reduce it to 0. That's when we reduce.
well, that's what, you've identified the bottom of T22, you gotta identify the top also. Then you know what T22 is, and then you go to work on it. Yeah.
Next entry.
Yeah.
If I hit a 0, that's where the top of T22 is.
Yes.
And if I don't hit a 0, then the whole thing is T22.
Yes, yeah, so then that way, in that case, there is no T11.
These are the type of coding problems that I actually enjoy, because it just seems like a giant puzzle, and as long as you can break it down piece by piece.
Yeah.
You're normally good, it's just you gotta break it down.
Yeah, yeah.
And I enjoy them, especially when they're slightly frustrating.
It's most definitely gonna beat that qualification. Yeah, because it's so easy to be like off by 1 or something. Yeah, so it's a good idea while you're getting this to work to have it print out like, okay, what did you come up with for beginning and ending rows of T22? To make sure it's picking it out correctly. And then does it change correctly as new entries become 0? Since I'm often talking about entries being 0 or non-zero, never, ever, ever check if some entry is actually equal to 0. It will never, almost never truly be 0 because of rounding error. Check if its absolute value is less than some tolerance. I think I specified in the assignment like 10 or minus 10, or you could, if you want to pick something more stringent, you certainly can. But yeah, you figure out this part, the rest of it's not gonna be so bad.
I learned that never check equal to 0 a very painful way.
Oh, yeah.
I was too stubborn to ask my professor why I was getting the problem, because everything I checked was working. I was like, it's not finding this thing. And eventually in class, someone asked them, and they're like, yeah, of course it's not gonna equal to 0. Print out that entry, see what it equals. I'm like, I did, it equals 0. So I changed the format.
Yeah,
And I was like, oh, God.
Yeah. Yeah, because it probably printed out 0.000.
Yeah.
In which case, yeah.
Yeah.
But yeah, the stuff like one of the things I have students do, you will see this in 560, where you do Gaussian elimination and you see the lower triangle is 0, but you notice that certain entries say 0.0000 and certain entries say actual 0. Like, what's the difference? Yeah.
At the bottom of T22, at the top of T22, when I start reducing it.
Yeah.
Do I do anything to T1? If there was a T1.
No, well, okay. Oh, actually, yes. So once, yeah, so if this decouples, once, at some point, you'll get around to T11 just for your natural searching. So I guess. So you don't explicitly have to deal with T11. It's just that by searching for the last unreduced block, you're gonna find it anyway.
Yeah, because when T22 becomes a 3x3, that'd be your last. iteration.
Well. Yeah, well, like this will eventually get absorbed into this.
Yeah,
Yeah,
And
Uh,
so.
yeah.
Everything D.
yeah. D3P will eat everything.
So, okay, this was my question.
Yeah.
This D that comes out here, is it the same D that's going in SimQR? No, wait, it's not going in, that's the output.
It's output of, yeah. So the D you finally get from this D that T gets reduced to is your output of SimQR and also the output of SimEig.
In SimQR, it's coming from
Tridiag.
TriDiag. Well, we're getting T and U from Tri.
Yeah. But you have to use U and the Q from here together to create the final Q that SimEig sends out.
U and the Q to find the Q.
Because I probably should just use a different letter for this Q, but
So it's the same.
Yeah.
Color.
Yeah.
So that step is happening between TriDiag and SimQR. U and Q.
Well, okay, so after you do tridiag, you just feed the T output to SimQR, get the diagonal matrix output, use SimQR's Q and tridiag's U to get the final Q that's output by SimEig that reduces A to try to diagonal form. Because this Q reduces T to diagonal form. You want the Q that reduces A to diagonal form. Okay.
So I'm starting with A. A goes in SimEig.
Yeah.
And A is going to call TriDiag first. So A goes there, we get U and T.
Yeah.
Out of this, T goes to SimQR
Yes.
and U goes.
You wait until SimQR finishes.
Oh, so SimQR takes in T and gives us D and Q.
Yeah, ask it again.
Takes in T, so this
Yeah,
guy.
yeah.
And gives us D and Q.
Yes. Now, but, okay, so then D is finished. Okay, now keep in mind, U reduces A to T. Then QR's Q reduces T to D. Yeah, and now you want a matrix that does all of it, that reduces A to D.
So we need the U.
And the Q. Yeah, and if you look at the various decompositions I wrote early on, you can see how to get the short decomposition of A. Yes, and how that relates to the decomposition of T from here and the decomposition of A from tridiag. So I guess think this way, you have U transpose AU is equal to T. U transpose EQ is equal to D, but I gotta label with Q tilde to distinguish.
That's what I did, yeah.
Then Q transpose AQ is also equal to D. Use these three equations together and you see how Q is built up from Q tilde and U.
Yes. Okay.
First was. Use. You and. The one that goes in there, Q equals I, that would be Q tilde.
Okay, this is an initialization inside SimQR, because Q is the accumulation of all transformations that happen in here. So you started about being identity, and then you're just multiplying it by stuff. Oh, yeah. There's a lot of fences flying at you.
So the accumulation matrix is what is going to reduce P to diagonal.
Yes.
Just one more thing. SimQR, that output will be D and Q tilde.
Yes. So, okay,
I'm just going to change it so. Out.
Okay. Okay, so I got all the tildes in place.
I'm not even writing that line, Q tilde equals.
Oh, okay, yeah, yeah. Oh, yes, it's a good say, it did say don't do that, but yeah.
Right.
Well, I'll make sure that I'm correctly telling you not what else to do.
Okay, then I need to use U and Q. Not Q tilde, but U and Q.
Oh, okay,
To reduce.
you, okay, U and Q tilde will, together will help you get Q. And then if you use these equations together, you'll see how.
Since 7:21, I've really started to enjoy writing book.
Wow, okay, cool. You just got a PhD in this stuff. So the very first time I gave this assignment is when it's 2001, and I've been away from Stanford for a while, still a student. And I came back, and my new advisor, Gene Gall, who had taken over from my previous advisor who was retiring. He had asked me to, because I was living far away, and he asked me to come back to Stanford to teach MATLAB class that they've been running. The class was normally taught by Catherine Muller, a professor in applied physics, and the daughter of the creator of MATLAB, Cleve Muller. But she was on maternity leave, so he needed someone to take over the class. So, okay, I'll do it. So, and I was trying to determine what I wanted to give them for like a midterm project, that sort of thing. And I covered how to compute eigenvalues using Eig. And the one student made this idle comment, like wondering how Eig works. How does it get the eigenvalues? I thought, you know what, that's a good idea for a project. So I gave him this. Except the main function, I did not call it SimEig. I called it, this is the actual M file, the big bad eigenvalue finder. That's what I called it, yes. Yeah, so I had them write the big bad eigenvalue finder.f. And so after implementing it myself, I thought, I want to see how this compares to MATLAB's implementation. Because I figured I was using a symmetric QR algorithm also. Now, back then, MATLAB had a command called flops that you could enter into prompt and it would tell you how many flops or floating point operations that had been performed during your MATLAB session. They got rid of it not too long after that because they had changed how MATLAB's lowest level operations were done. And I guess it'd be too much of a drag on performance to also count flops. So like, dang it. Because I liked having a command around because after I spent several hours doing stuff in MATLAB, I could type flops and it gives you this big number, like if I perform like, billions of flops and you feel productive. So, and I also loved how if you hadn't done anything yet, it would say 0 flops. It would spell out no flops. Or if you've done one operation, it would say a single flop. So after I implemented symmetric Q algorithm, I thought, okay, I'm gonna see how many flops it takes, and then call I on the same matrix and see how it does. And of course, theirs is better. It's like, dang it. So, but I tried to optimize my code as much as I could, and I actually got pretty close. Like, well, it was still like 40% more. But I was like, oh, okay, getting there. So, yeah, but now I can't do it anymore. So. But it makes you wonder, like, maybe we weren't doing exactly the QR algorithm as in textbooks, but maybe some tweaks of it that you can probably find in some published papers or something. So yeah. One thing I never have done, I should try it out, is if this is for an unsymmetric matrix, so you're doing like a Francis QR step stuff and all that, but then actually doing what Ike does, which is get the eigenvectors also. The thing is, there's no guarantee you're going to get the eigenvectors, and you're trying to, you've reduced A to upper triangular form or quasi upper triangular form, but now you want to reduce it to diagonal form if possible. So, but you're not using orthogonal similarity transformations anymore, because you've gone as far as you can with that, and so it is discussed in Golub Van Loan, like in chapter 7, how to get the eigenvectors, but it's a lot of overhead. So, and I honestly don't know how they handle the case where matrix is not diagonalizable, because I think what MATLAB does is, it'll for an n by n matrix, it will still give you a matrix consisting of n eigenvectors, but that matrix is going to be singular. Because if it's not diagonalizable, it means you don't have n linearly independent eigenvectors. So it will give you a matrix X so that AX equals XD, but in that case, you can't do X inverse AX equals D because X is not invertible. So, and as I mentioned at the beginning of the eigenvalue chapter, it'd be nice to get to Jordan form in that case, but since it's not the continuous function of the matrix entries, you can try it, but you don't know if it'll be reliable. So. Okay, so any remaining questions about this? So Dale, has this induced you to do it or not do it?
I still haven't decided.
Okay, well, you have time. I guess I'll matter looking at the upper option too. So. Okay. Well, so then on Thursday, I'll cover the SVD algorithm, and that'll end eigenvalue coverage. Yeah, so my advisor's algorithm basically. So until then.